Cross-section of collisions. Imagine a scenario in which we have hard spheres of area sigma with density n. Beam of particles is incident on this target. Beam has area of A, and the thickness of the target is given by L. We want to know with what probability will the beam of particles interact with the hard spheres. We can recognize that the probability is simply given by the ratio of areas covered by the spheres and the beam area. The area covered by the spheres will simply be given by the density of the spheres times the volume of the target times the cross-section of each sphere divided by the beam area A. Obviously, the volume is simply area times the thickness of the target, which gives us the following expression for the probability. Density n times thickness of the target times the area of each sphere, sigma. Note that this is a 3D density, whereas we can also introduce target density and target, which is going to be the density of spheres times the thickness of the target. And so we can rewrite the probability as simply as density of the target times the cross-section. Note that this density of the target is 2D, areal density. We can ask the question how many collisions will occur, and it depends on how many incident projectiles go through the target. Number of scattering will be given by the number of incident particles times the probability of each particle interacting with this hard sphere, which is simply the density of the target times the cross-section. Likewise, the rate of scattering, which we can denote as dot of the number of scattering events, will be given by the rate of incident projectiles times the density of target times the cross-section. Next, let's consider what happens to the beam intensity. By beam intensity, we understand the rate of projectile particles divided by the area. The change in the number of projectiles per unit time will be simply given by the number of scattering events per unit time, which is given by minus IA times the cross-section times the density times the thickness element dl. Canceling out the area, we can write this equation as di over I equal to minus sigma density times dl. Next, we can integrate this expression. We will integrate it from 0 to length L, and we expect the initial intensity I0 and final intensity I. After integration, we get logarithm of I over I0 is given by minus sigma NL. Or we can write it as intensity as a function of thickness L will be given by I0 times E raised to power of minus sigma NL, which we can further write as I0 exponent of minus L divided by lambda, where lambda is defined as attenuation length and is given by sigma times n raised to power of minus 1. Let's mention some additional properties of cross-section. We talked about different reference frames: center of mass reference frame and the lab reference frame, or the target reference frame. And the question is, how the cross-section in the center of mass and in the lab reference frame relate to each other? Well, clearly, since cross-section is related to the number of ends that doesn't depend on the reference frame, we can see that cross-section is not a function of reference frame. It's the same in either reference frame. This is true only for total cross-section, not differential cross-section, that we will talk about in the next video. Another property of cross-sections is that they behave as probabilities. So if we consider different mechanisms for scattering, for example, absorption or capture of particles, to find combined cross-section, we simply add the probabilities.